Welcome to the Ontario High School video podcast having to do with stoichiometry and particularly the use of BCA tables in the solving process of stoichiometry problems. The BCA tables, if you're not familiar with them, may seem at first to be kind of bulky, but if you can learn to use them with the simpler stoichiometry problems, when we get into more complex problems such as limiting reactant problems, they'll really simplify your life. So welcome, and here we go. The first type of stoichiometry problem that we're going to do has to do with starting with moles of a reactant and finding moles of either another reactant or product that isn't given to you in the problem. So this first problem, the most important thing to do that affects everything is to make sure the equation is balanced. But let's look at the problem. Hydrogen sulfide gas, the formula for that is H2S, which smells like rotten eggs, burns in air to produce sulfur dioxide and water. How many moles of oxygen gas would be needed to completely burn 2.4 moles of hydrogen sulfide? So below us is the balanced equation. 2H2S plus 3O2 will yield 2SO2 plus 2H2O. If you struggle with balancing equations, please check the Moodle page or check with your instructor because there are some wonderful podcasts that will help you to balance equations as well. So again, you want to make sure that the equation is balanced, and we're ready to go here. So next step, following slide. Once we have the equation balanced, we're ready to set up the BCA table and fill in the before line. Now BCA represents B is before, C is the change that happens in the chemical reaction, and after is what you have when the reaction is completely done. And all quantities in the BCA table are in moles of reactant or product. That is critical for us to understand. We don't put mass values in, we put mole values. And the reason for that is we cannot compare quantities directly of reactants and products in mass, but we can compare the quantities directly in the mole. So we want to use the mole as a unit in the BCA table. So we know that we have 2.4 moles of H2S. For the O2, we need to find that, and actually we're going to replace the question mark that you see here with a term called XS, and that XS is going to imply that we have more O2 than we need, so we have it in excess, hence we use the XS. So we will be replacing that question mark soon. We assume at the beginning of the reaction, before it starts, we don't have any of the SO2 or the H2O. And so again, our assumption is that we have more than enough O2 to completely react the H2S. Next, we're going to fill in the change line, and we're going to use the mole ratios to calculate these as needed. We know how many moles of H2S that we have, so we're going to use the mole ratio between H2S and O2 and SO2 and H2O to fill in the amount that changes. So you can see below the calculations are done. We know that H2S is the limiting reactant. When you're only given the amount of one reactant, that's going to be the limiting reactant. If you're not given the amount of any of the others, then you just have to assume that what you're working with is the limiting reactant, and it will determine what the change values are. So we take our 2.4 moles of H2S and we multiply it times the mole ratio of O2 to H2S, which is 3 over 2, and we get that we're going to need 3.6 moles of O2. That's how much the O2 is going to change by and how much is needed to completely react the H2S. Now, the good news in this problem is that the mole ratio of H2S, SO2, and H2O are all the same. So the amount that H2S changes will also be the amount that SO2 and H2O change, except in the opposite direction. You're going to use up the H2S, so we have a minus 2.4 moles under it, but the SO2 and the H2O are going to change by plus 2.4 moles. Now, I did the mole ratio calculations below so that you could see them as a proof, but when the mole ratio is the same, the amount of change is the same either in the positive or negative direction. So that's just something that can help you save some time as you go through your calculations. Our next step then is to fill in the after line, what's left over. Here you'll see that we finally have the excess in the before line for the O2. We know that the H2S will change by minus 2.4 moles. The oxygen, which is in excess, will change by minus 3.6 moles. The SO2 and the H2O respectively will change by an increase of 2.4 moles. So the after line is just the before line, either minus or plus the change, depending on whether it's a reactant or product. So H2S, we're going to have 0 left because 2.4 minus 2.4 is 0. Our excess, we subtract 3.6 moles from it, and we know that we're going to have some left over, but because we didn't know our starting amount, all we can put is that there is excess O2 left over. Our SO2 and H2O both are 2.4 moles. So when we go to solve for how much O2 we needed in moles, we can look in that change line and it will tell us we needed 3.6 moles of O2. 3.6 moles of O2 was required to completely react the 2.4 moles of H2S. The converting from moles of one reactant or product to moles of another reactant or product is the simplest type of stoichiometry. Most of the time, because in the laboratory we really don't have balances that measure moles directly, we measure mass, normally in grams. The mass stoichiometry that we're going to look at now is much more common. So let's consider the same problem as before, except we're going to have a starting quantity in grams rather than moles. So here we have hydrogen sulfide gas, which smells like rotten eggs, burns in air to produce sulfur dioxide and water. How many grams of oxygen gas would be needed to completely burn 41.8 grams of hydrogen sulfide? The equation is given as H2S plus O2 yields SO2 plus H2O. And why don't you go ahead and balance the equation, and we'll start on the next slide. So here we go. Step one of any stoichiometry problem is to make sure the equation is balanced, and it is 2H2S plus 3O2 yields 2SO2 and 2H2O. And you're thinking to yourself, we did that before. It should have been pretty easy to get. Why would you do that to us? Simply because getting a problem right is always fun. So I hope you had some fun with that. And now we're going to go on to step two. Our next step is to set up the BCA table and fill in the before line. To do this, because we only put mole quantities into the BCA table, we need to convert the grams of H2S to moles. The conversion is shown below, are 41.8 grams of H2S times the equality of 1 mole of H2S for every 34 grams of H2S. We sometimes also call this a conversion factor as well as an equality. So depending on who your teacher is, you'll hear those terms interchangeably. When we do this, we get 1.23 moles of H2S, so we put that into the before. Our oxygen is in excess, and we have 0 SO2 and 0 moles of H2O to start. As we did before, since we have our value of H2S in moles, our quantity in moles, we can now use mole ratios to calculate the values in the change line. So we take our 1.23 moles of H2S times 3 moles of O2 over 2 moles of H2S. Remember, you always get the mole ratios from the balanced equation, and that gives us 1.84 moles of O2. Our 1.23 moles of H2S times our 2 to 2 mole ratios for H2O to H2S and SO2 to H2S mean that we're going to change by plus 1.23 moles for each of the sulfur dioxide and the water, the SO2 and the H2O. Remember, when the mole ratio is the same, it really makes the BCA table calculations quite easy. Well, step 4, we're ready to fill in the after line of the BCA table by subtracting or adding the change from the before line. We subtract if it's a reactant being used up, we add if it's a product being formed. So for the H2S, we take 1.23 minus 1.23. We have 0 H2S left at the end of this reaction. For our O2, we know that we're going to use 1.84 moles of it. So we have our excess minus the 1.84 moles. We still don't know how much we have left over because we don't know how much we started with. So we just continue to put excess there. our SO2 and H2O both increased by 1.23 moles. So from 0 plus 1.23, we have 1.23 moles of each of those. What we were trying to find was the number of grams of O2 we needed. We now know the number of moles. 1.84 moles of O2 are needed to react 1.23 moles of H2S. We have to find moles first before we can find the grams of O2. You can think of the mole calculations as the bridge to go from grams of one to grams of the other. You're going to have to use a mole ratio calculation as part of that bridge. The last step is to convert the moles of O2 to grams of O2 because that's what the problem asks for. So I have 1.84 moles of O2. I know that from my BCA table. That's how much I needed to use to completely react the H2S. So I take my 1.84 moles of O2 and I multiply it times my conversion factor or equality that relates grams of O2 to moles. So 1.84 moles of O2 times 32 grams of O2 over 1 mole gives us 58.9 grams of O2 are needed for this reaction. So that is how you do mass-mass stoichiometry. The next slide is going to show you a rather condensed version of this, but it gets you to the same place. If you're not from Ontario High School, you may not have an instructor who uses BCA tables. BCA tables are a wonderful tool, especially when it comes to limiting reactant stoichiometry, but oftentimes you'll be taught a method in mass-mass stoichiometry where you'll simply convert from grams. In the case of this problem, you would convert from grams of H2S to moles of H2S, then multiply that by the moles of O2 over the moles of H2S to get to moles of O2, and then finally convert from moles of O2 to grams of O2. This can be done in a single three-step conversion factor setup, and I want to show you that below. So we write down our starting amount, 41.8 grams of H2S, and we use the first conversion factors to take us to moles of H2S. So it's times 1 mole of H2S over 34 grams of H2S. If we were to stop here, the grams of H2S would cancel. You'd be left with moles of H2S. And you know that if you have the moles of any reactant or product, you can find the number of moles of any other reactant or product simply by multiplying by the mole ratio. So our next conversion factor is the mole ratio, which from the balanced equation is 3 moles of O2 for every 2 moles of H2S. Here you would cancel your moles of H2S. You're left with your moles of O2, and now you simply have to use the conversion factor to go from moles of O2 to grams of O2, which would be 32 grams of O2 over 1 mole of O2. When you do that, you'll get a quantity of 59.0 grams of O2. I generally multiply everything across the top, so it'd be 41.8 times 1 times 3 times 32. Hit the enter sign on my calculator or equal, and then divide individually by the bottom. So it'd be divided by 34 grams of H2S, hit enter, and then divide by 2 moles of H2S, hit enter, divide by 1, hit enter. When you do that, you end up with 59.0 grams of O2, which is very, very close to 58. Well, we've come to the end of part 1 of the podcast. Want to leave you with a quote from a famous Native American chief, Standing Bear, who said, "Man's heart away from nature becomes hard." I wish you well. Stay tuned if you have doubts or this is really difficult for you. The BC